First of all, an augmented matrix for a system of equations is just where you choose to rewrite the system of equations, but you don't write plus signs. You still write the minus signs. But we don't write plus signs, we don't write x's or y's, and we don't write equal signs. So if I wanted to write the augmented matrix for this system of equations, we'd get 7, 3, 32, negative 4, 1, negative 40. Once we have our augmented matrix, we want to row reduce. And so the goal of row reducing is you write 1, 0, 0, 1 in the first two columns. And if you can manage to get that, your rightmost column is going to contain the solutions to your system of equations, x and y. When you're row reducing and trying to get here, there's only 3 allowed row operations. There's 3 things you're allowed to do. You can add or subtract one row from another. You can multiply or divide a row by a constant, and you can swap the position of rows. There's things you're not allowed to do, though, right? I don't want to be super clear about this. You cannot multiply or divide 2 rows, right? I would not be able to say row 1 times row 2, right? Not allowed to do this. You can only multiply or divide by a constant. You also can't multiply or divide by 0. You can't divide by 0 because that's not defined. And you can't multiply a row by 0. Otherwise, you would lose some of the information in the problem. You just get a row of 0, 0, 0. We don't want that. So I specifically wrote, you can multiply or divide a row by a non-zero constant. And this seems to be a point of confusion sometimes. I can add or subtract one row to or from another row, but you cannot add or subtract a constant number to or from a row. So I can't just say row 1 plus 5. That doesn't work. So we'll do one more example, and then we'll move on with new content for today. This example is a little bit tricky. It takes a few extra steps to get started, and so I want you guys to see what a trickier example might look like. Whenever I look at this augmented matrix, my first thought going through my head is, I want the top left entry to be a number 1. I want the number 7 to be a number 1. Ideally, you would be able to do this by adding or subtracting the second row. But we cannot do that in this case. It's a little bit trickier. I can't just add negative 4 and get a 1. If I added negative 4 twice, I'll get a negative 1, so I kind of overshoot a little bit. Another way you might sometimes be able to get a 1 is you could divide the top row by the number 7. Okay, 7 divided by 7 is 1. But I don't want to do that in this case because I would get 5 divided by 7, which is a fraction, and I would get 19 over 7, which is a fraction. And I don't want to have to deal with fractions. If that's the case, and you can't think of a way to get a number 1, maybe you move on and you think about, how could I make the negative 4 into a 0? And I can't multiply by 0, but maybe I could add the first row. Well, in this situation, I can't really add 7 to negative 4 and get a 0. So there's really no way for me to get a 1 or a 0. If you can't do that, right? If I can't really seem to get either the 1 or the 0 right away, then let's at least get a little bit closer. And what I mean by that is I could replace row 1 with row 1 plus row 2. And it's not going to give me a 1 in the top left corner, but at least I'm getting a little bit closer, right? So this top row is going to be 7 plus negative 4. That's 3. 5 plus 2, that's
6, 7.
And then 19 plus negative 40, negative 21. All right. The second row can stay the same for this step. And then the next thing I'm thinking about is, could I make that 3 into a 1? I could divide by 3. Oh, crap, except still the 7 is causing an issue. I don't want to have 7/3. So I'm not going to try to divide by 3. The next thing I might think about is if I can't get a 1 here, maybe I could get a 0 for the -4. Crap, but again, I cannot add 3 to get a 0. It's only going to give me a -1. If I were to add 3 twice, I get a +2. I just can't get a 0. In this situation, maybe I could still get a little bit closer. I can't get a 0 right away, but maybe I could get a little bit closer. I'm going to go ahead and just try to replace row 2 with row 1 plus row 2. So row 1 stays the same. And this time, what's my bottom left entry? -1. And then bottom middle? 9. And over here? -61. Very good. So again, I've had to take some steps here already. And unfortunately, I still haven't been able to get a 1 in the top left or a 0 in the bottom right. But at this point, after doing a little bit of work, now could I get a 1 in the top left corner? Yeah. How do I do that?
Minus row 2 times 2.
Perfect. I could replace row 1 with row 1 plus row 2 times 2. And then I would get 3 plus -1 times 2, which is 3 plus -2. 7 plus 9 times 2. That's 7 plus 18. 25, yeah. And over here, a little bit trickier, but I can write it down to be extra careful. And you can also use a calculator on your test that's coming up. It's 1 week from Tuesday, by the way. It's not next Tuesday, but it's a week from Tuesday. On that test, you can use your calculator, and so you could type in -21 plus -61 times 2, and the answer here is perfect, -143. The second row gets to stay the same in this step. And that's good. I finally made some measurable progress. It took a while. We had to think about it a few steps and just kind of try to inch closer to it. But eventually we did get that 1 in the top left corner. Now I want this -1 to be a 0. And so I should replace row 2 with what? Yep. Row 2 plus row 1. That would do the trick. So -1 plus 1 is 0. 9 plus 25 is 34. And then -61 plus -143 would be -204. Cool. And we're doing really well. I've got a 1 in the top left. I've got a 0 in the bottom left. How do I make this 34 into a number 1? Yeah. Very good. If I take row 2 and I divide row 2 by 34, I would get 0 divided by 34 is 0. 34 divided by 34 is 1. And -204 divided by 34 is -6. We're very close to being done here. The last thing I need is to make that 25 into a 0. So what should I do to get a 0 right here? Yep. I'll take row 1 minus row 2 times 25. So 1 minus 0 times 25 is 1 minus 0. 25 minus 1 times 25 is 25 minus 25. And then the last thing you might want to write down, because it's a little bit trickier, and you might want to plug this into your calculator and really think about it, just to make sure we don't make any mistakes. This would be negative 143 plus 150. So it's 7. So we are done row reducing when we get to 1, 0, 0, 1. And my solution would be x equals 7 and y equals negative 6. This is my solution. I know that there's an x value and a y value, but we still call this our solution in like the singular. We don't say that's our solutions. It's really one solution where these two values satisfy this system of equations at the same time. But again, I just thought I would give you one more example, both to refresh you on what we did earlier this week, and to give you an example that was a little bit tough, because again, this was only tough because I couldn't immediately get a 1 in the top left. I couldn't immediately get a 0 in the bottom left. I had to do a few steps before I was finally able to get that 1 in the top left. So sometimes you gotta try different things. You gotta be patient with it. Sometimes you make a mistake. You do the wrong thing. You gotta erase it, start over. But eventually, keep working on it. You might find a path forward. There's one thing that you could do to solve a system of equations that we haven't talked about yet. And that is you could graph both of these equations. And since these are linear equations, these equations are going to graph as lines on the xy plane. And the solution to your system of equations is going to be the x and y coordinates at the point of intersection. So you should have two lines on your plane. They intersect somewhere. And at this point, if you just read off the coordinates, that's your x value and your y value that's going to work for your system of equations. So that's an option. In fact, on your next test, you might even want to bring a ruler. That way you can draw straight lines better. And with a straight line, you get a more accurate answer. I'm going to do my best to draw lines here, but I don't have a ruler handy. Let's solve this system of equations, which is the same one as in the previous example, but this time we're going to solve it by graphing, and you can see what that would look like. I have shown this method before last week, but it may have been that day where my lecture went a little bit long, and so this might be the first time you're seeing it. But here's the idea. I look at this equation given to me in general form, and I think, what would happen if x is equal to 0? If x equals 0, then my equation becomes 5y equals 19, which means y equals 19 fifths. And 19 fifths, that's just 3 plus 4 fifths. And I know where to put this on my xy plane. I have to say x is equal to 0, so I'm right here on the y-axis. And along the y-axis, I'm going to find the point that's 3 plus 4 fifths. And I can graph this blue point here. And I know that has to belong to my line here in blue. I could also use this equation to say, what happens when y is equal to 0? If y is equal to 0, then this equation gets to become 7x equals 19. And that means x is equal to 19 over 7. 19 over 7 is also the same thing as 2 plus 5 over 7. And that helps me graph this point. This point happens when y equals 0. So that puts me on the x-axis. And along the x-axis, I'm going to find the point where x is 2 plus 5 sevenths. So it'll be like right here. on my plane. And now the great thing about this method is any 2 points is going to fully and uniquely define a line. In other words, there is only one line that passes through both of these 2 points. And if you want to draw this line, you just take your ruler, or if you don't have a ruler, you might use the edge of a piece of paper. Just line up the edge of your paper so that it lines up with both of your points here. And then you just, draw a line through them. I don't have any way to do this, so I'm just going to try to draw the best line I can from connecting these dots. Oh, that's pretty bad. I'm going to try to connect the dots. And then try to extend this line as straight as I possibly can make it. Hopefully it's good enough. Usually it's not good enough unless you're using a straight edge. It's really hard to draw straight lines. Okay, then this next equation here. Let me try the same approach and see if it works. Let's say x is equal to 0. This equation would be 2y equals negative 40. And I could say y equals negative 20. That means along my y-axis, when x is equal to 0, my y-intercept is negative 20. But that's like way down here. I don't have room for that, so I can't really use that point. It's kind of no good. Well, I can still try what happens if y equals 0. If y equals 0, then this equation is negative 4x equals negative 40. And if I divide by negative 4, that gives me x equals 10. So right here, when y is equal to 0 and x equals 10, I can put that dot down. But I still don't have enough points to draw a line, right? I need 2 points in order to draw a line. And I might have to choose another point around here. So I might say, what happens if x is equal to, I've already got x equals 10, and I know x equals 0 ends up way down here. Maybe something in the middle like x equals 5. That could give me a point that's maybe on this part of the graph. And if it doesn't work, I could just choose a different value for x. But I'm just trying to get one more point. And it doesn't matter really where it is as long as it ends up on my graph. If I look at this orange equation and I say x equals 5, that's negative 4 times 5 plus 2y equals negative 40. In other words, negative 20 plus 2y equals negative 40. And if I add 20 to both sides, this is 2y equals negative 20. And if I divide both sides by 2, y is negative 10. All right, so if x is 5, y is negative 10. So I can place a dot right here. And that's great news. I've got 2 dots. I can line up my ruler and draw a straight line through these 2 points. And if I try my best, it's going to look maybe something like this. And I have 2 lines. 2 lines that represent these 2 equations. Like I promised, the point of intersection right here between these 2 lines, it has an x-coordinate of 7, and it has a y-coordinate of negative 6. So based on the coordinates here at my point of intersection, that should hopefully give me the right answer to my system of equations. If you have a system of linear equations, you've got 2 equations with 2 unknown variables, like x and y. And this is basically the situation we've seen all week long. There's actually 3 possible categories. And so far this week, you have only seen an independent system of equations. This is the only category we have witnessed so far in your homework and during lecture. Independent system of equations are great because you get a solution. You only have one unique solution. You can always find it. And whenever we graph this on an xy plane, you end up seeing 2 intersecting lines where their point of intersection is that one unique solution. Okay? The other categories that we're going to see today, we call them dependent systems of equations. And these are not very nice. We'll see an example that's going to kind of make this make more sense. But you'll see 2 equations that look different when you just glance at them. But if you actually go to try to graph these, you'll find out that both equations are still describing the same line on your xy plane. And for that reason, there's actually infinitely many points that lay on both lines, and so you have infinitely many solutions to your system. We'll talk here in a minute about how you might identify this. But you could have independent systems, you could have dependent systems, and then the third category is called inconsistent. And an inconsistent system of equations is one where there is no solution at all. Geometrically, what happens is you go to graph this, and you graph 2 lines that are parallel to each other. That means they're going to have the same slope, but they're going to be spaced a little bit apart. And if they've got the same slope and they're parallel lines, they're never going to intersect each other. And if they don't intersect, there's no point of intersection, and there can be no solution to your system of equations. And so we'll also see an example of this today. 3 categories. The easiest way to distinguish, if you've got a system of equations, you're like, which category does this fall into? The easiest way to tell is to try to graph it. Graphing it is going to be the fastest way to tell whether your lines intersect each other, whether your lines are parallel, or whether those 2 equations are actually trying to describe the same line in space. That's the easiest route. But if you don't have graph paper, or if you just don't have the time, maybe you just don't want to graph, you could actually still distinguish these cases from row reducing. And this is the idea. If you are able to row reduce your augmented matrix, and you actually get a solution from row reducing, then you know you are dealing with an independent system of equations. So you row reduce, you're using only the allowed row operations. That's what you should end up with. Okay. What if you are row reducing and you're using only your allowed row operations, but you end up with a row of all zeros? So you've got some first row going on, but then the second row might be 0, 0, 0. Again, you can't multiply a row by 0, but this just might happen using the operations you're allowed to use. If you've got this row of all zeros, that's how you know you're dealing with a dependent system of equations. That's one way to tell. And lastly, maybe you are getting an augmented matrix, you're trying to row reduce using only the allowed operations. You might end up with a situation with a row of 2 zeros and then a third value in the last column that's not a 0. Like maybe your last column is 0, 0, 6 or 0, 0, negative 1/2. If you end up with that situation, this is telling you it's inconsistent. And you can't possibly have any solution to this system of equations because this last row is representing an equation. the equation that this last row represents is 0x plus 0y equals 6. And you'll notice that no matter what values you choose for x and y, you can never make this equation valid, right? It's always going to be 0 on the left side, 6 on the right side. And that's why we say there are no solutions if you find a inconsistent system of equations.
It doesn't have to be the bottom row, right? It can be the top row, like 0, 0, 0.
Yep, you're right. If you found a row of all zeros in the top row, that's dependent. If you find a row of 0, 0, something else in the top row, that would also be inconsistent. Good question. So let's take a look at an example. And this is what your homework looks like. It normally says, solve the system of equations using both methods. You know, when I say both methods, I mean use the augmented matrix and row reduction, and then separately try to graph these lines and see what you get. And this time we're going to state whether or not the system is independent, dependent, or inconsistent. I'm going to start off by writing the augmented matrix and then trying to row reduce here. That is my augmented matrix. And when I think about row reducing, I think to myself, could I make that -2 into a +1? And ideally, I'd be able to add the second row and get a +1, but that's not going to work, right? If I add 6, it's going to overshoot. It's going to give me a +4. That doesn't work. I could try to take the first row and divide by -2, but if I did that, I would end up with 3 halves, right? And I don't want fractions. If there's no way to get a +1 in the top left corner, I'm just going to move on and I'm going to think about how to get a 0 in the bottom left corner. Can I turn that 6 into a 0? Perfect. You're right. If I take row 2 and I add row 1 3 times, so I do replace row 2 with row 2 plus row 1 times 3, then row 1 gets to remain the same in this step. And row 2 is now 6 plus -2 times 3, so 6 plus -6. And then the middle bottom entry is 9 plus -3 times 3. 9 plus -9, that's 0. And then the last entry is -9 plus 3 times 3. That's 0. What does it tell you if you've got a row of all zeros? This is dependent. Yeah, and notice I didn't multiply by 0, but I only used my allowed row operations, and I still got a row of all zeros. That's how I know this is dependent. The next thing I want to do is try graphing it. And so let me try graphing this first equation. And I'll use a different method of graphing than I did last time. This is called the general form of the equation. This time, when I graph, I'm going to solve for y first. And I'm going to add 2x to both sides. And to solve for y, I would want to divide both sides by negative 3. And now this is called slope-intercept form, because I can tell the slope is negative 2/3, and I can tell that the y-intercept is negative 1. So here's my y-intercept of negative 1, and since the slope is negative 2/3, I can go down 2 units, across 3 units, put a dot, down 2 units, across 3 units, and put a dot, down 2, across 3, put a dot. I'm going to connect my dots to make a line. And then I know this is going to be a straight line, so I can also extend this in the other direction using the same slope. And maybe that's easier, right? It's kind of up to you. But that method might be easier and a little bit more precise for graphing lines. What we're doing is we're taking the general form of the equation 6x plus 9y equals negative 9, and then we're going to solve for y to give us the slope-intercept form. This time I'm subtracting 6x from both sides. And then I'm going to divide both sides by 9. And then I'm going to simplify the fraction. So negative 6 over 9 simplifies to negative 2/3. And of course 9 over 9 is 1. And I say, okay, my red line is going to have a y-intercept of negative 1 and a slope of negative 2/3. But you might actually notice I'm about to graph the same line. The blue equation and the red equation looked different at first. But when you actually put it in slope-intercept form and you try to graph this thing, you find out you're graphing the same line. In the cases when you have a dependent system of equations, you might find out, because you're finding a row of all zeros when you try to row reduce, and you might find out because you graph the same line when you're graphing the lines. In either case, I want you to actually say the word dependent. Not out loud, but you would write this down on your test paper. And then I also want you to write this equation. I would like you to write y equals negative 2/3 x minus 1 whenever you get the dependent case. Any questions about how we knew this was dependent, or how we graphed those lines? Does that make sense? It's the same exact question, but it's a different system of equations. And so we're going to take the same approach. I'm going to write the augmented matrix down. And then I'm going to try to row reduce. So in the process of row reducing, I start to think, is there any way I could make that 5 in the top left corner into the number 1? So the first thing you should try is try to add or subtract row 2. But if I add 10, I get 15. If I subtract 10, I get minus 5. It's not going to work out. The next thing you could try is, what if I took row 1 and I divide row 1 by 5? But I don't want to do that because I don't want to get negative 4/5. I don't want to get any fractions. So let's not do that. I have to give up on the 5. And I'm moving on. I'm thinking about the 10. I think, is there any way I could make that 10 into a 0? Yeah. What if I replaced row 2 with row 2 minus row 1 times 2? So row 1 gets to remain the same. And row 2 gets to become 10 minus 5 times 2. 10 minus 10 is 0. negative 8 minus negative 4 times 2, that's negative 8 plus 8, 0. And then I got negative 4 minus negative 5 times 2. So that's negative 4 plus 10. That should be 6. Right? So if I have a situation where one row in my matrix is 0, 0, but the third column has something non-zero, in this case 6, that row tells me this is, yeah, exactly, inconsistent. And if it's inconsistent, think about what this row is telling us. That row is trying to tell you 0x plus 0y equals 6. But there are no solutions to this equation. There's no values of x and y you can possibly choose to make that work. So as we call this inconsistent, we say there are no solutions. And we're going to try to graph this thing. I'm going to use the same method as before, where I put this into slope-intercept form. And that means I would solve for y. So I subtract 5x from both sides, and then I divide by negative 4. So this is actually 5 over 4x plus 5 over 4. Once you're done putting that into slope-intercept form. And so I've got a y-intercept of 5/4, which is right there, and a slope where I go across 4 units and then up 5 units. And I'm going to put a few dots down so that I can try to graph this line as best I can, trying to connect these dots. Sorry for the squiggliness. Now let's look at this line. I'll get, I'm taking the red line in general form, but I'm rearranging it to get slope-intercept form. I'm really doing the same thing I did before. So if I want y by itself on the left-hand side, the first thing you would do is subtract 10x from both sides, and then divide by negative 8. And I'm going to get 5 over 4x plus 1/2. So my y-intercept of the red line is 1/2. It's right there. And the slope is going to be 5 over 4. So I get to go across 4 units and up 5 units. And again, maybe you notice that these lines have the same slope, but they have a different y-intercept. So they're going to have the same slope everywhere I look. The difference is that the red line is just a little bit lower than the blue line. And since they have the same slope, they will maintain the same distance from each other, no matter how far you trace them. And so if lines maintain the same distance from each other, they never intersect each other. That's what we call parallel lines. And since they don't have a point of intersection, they don't have a solution.